All right, good afternoon. Can you guys hear me? Okay, well, thank you so much for joining. I know it's Thursday, it's the last session. Apparently, Ali told me personally that they saved the best for the last. So thank you all for coming. I think we're about 35 or 40 in the room. The topic today is automating taxonomy generation with compound AI / agents on Databricks. My name is Sudhir. I head up the Gen AI practice at Lovelytics. With me, I have my colleague Alistair. He's a lead consultant in our team. I am good at making slides. He's good at writing code. So we make a good team. So hopefully this will be a fun session. I'm sure you guys have seen this. You are fully aware of this. Would truly appreciate, oh, there was a feedback slide. Would truly appreciate if you guys can give us some feedback. So the agenda is kind of divided into 3 sections. I'll talk a little bit about taxonomy, origin, importance, why, all of that. I'll talk a little bit about the compound AI / agents, what is all that about. And then Alistair will bring everything together for us from a compound AI for taxonomy perspective. You'll get to see a pretty cool demo as well, and then we'll kind of conclude. Hopefully, if there's time at the end, we'll take the questions. If not, we'll be hanging around, so please feel free to ask us questions. We have done several implementations of compound and agentic systems, so we'll be happy to share any feedback, any information, knowledge we do have. All right, so having said that, when I first got into taxonomy with the client several actually months back, and I started to research, I kind of realized that the roots of taxonomy literally go back like thousands of years during the times of Aristotle in the ancient civilization. In the recent past, which is about 1700s, Carl Linnaeus, father of modern taxonomy, created the binomial nomenclature and the hierarchical structure still used today. So obviously, taxonomy is as relevant today as it was back then. I mean, we all know a proper taxonomy serves as a shared language, creates consistency in naming and classification, helps reveal relationships, which can then further drive search and discovery. Again, in today's world with AI, classical machine learning, Gen AI, we can all appreciate the meaning of a well-structured, detailed, and curated data. Hence, taxonomy is very important, very relevant today. Obviously, I have to kind of mention this, as the famous philosopher Confucius said, beginning of wisdom is to call things by their proper name. I think that's pretty important quote over there. Claude Shannon, father of information technology, best way to understand something is to organize it. Now, I personally come from a background decades ago in relational systems where everything was structured. There was a technique called normalization where you would take data, organize it, structure it. So that importance, even though we live in a world of highly unstructured data, still exists. All right, so the business impact of taxonomy, right? So when we worked with real clients in retail and manufacturing, kind of becomes apparent to us that in today's world, it serves as the foundation for structure, organization, and meaning. First of all, it enables consistent categorization across systems. And I have yet to meet a client who has one system and one system only. I know many clients who have like several ERPs, several relational databases, several data warehouses. So as you can imagine, this takes a very, very kind of important significance. It is hard to piece a complete picture when you have like missing data or incomplete data, right? How can you do analytics or predictions or any of that type of stuff when you don't have all the information kind of pieced together? And as I said, when we work with customers in manufacturing, retail, e-com, they mentioned that taxonomy is a very, very critical problem for them, right? It actually impacts business function. It impacts economics. We have seen a very recent client use case where they completely express their inability to upsell and cross-sell to their clients because they just don't have a complete picture of who the retailer is or who the client is. So obviously, it's got huge impact. The other thing we realized is, working with business experts, is taxonomy is not a one-time task. It's not like you can sit down in a room for like a week or 10 days and get the whole thing done. Why? Businesses change, new products come in, you launch new product lines, new customers come in. So obviously it has to be kept updated on a regular basis. Hence, it is very important to have some sort of automated system, some sort of AI-driven system, ideally in our world, which can keep things automated. So having said that, what are some of the typical challenges, right? I mean, it is important, we know that, having a great taxonomy, a great classification would be good, but why is it so hard? So traditionally, taxonomy was sort of like a byproduct, right? Or rather, an afterthought, I mean. And it was always done manually. So there was no systems per se. I mean, a lot of the ERP systems will have metadata tagging and stuff like that, but it was almost like an afterthought. Not only that, different people across different business groups are responsible for taxonomy in a typical and traditional system, so that leads to inconsistent classification, inconsistent tagging. We all are data people in the room. We know exactly what happens when the same thing is called by two different labels, so on and so forth. Scalability becomes an issue, right? Most of the clients we deal with in retail or manufacturing or whatnot have tens of thousands of products. And the other interesting thing is, if you use traditional software techniques, which are typically rule-based techniques, it's very hard to come up with rules to generate taxonomy. But guess what? Modern AI, especially Gen AI using multimodal approaches, which you will shortly see, as I said, he's the real smart guy. You will see a cool demo where we are doing multimodal things and all that type of stuff. Semantic search, semantic similarity, vectorization, all those kind of techniques now help you piece together a almost near perfect or a near accurate taxonomy picture. So when we did this project, I think some of the analysts told us that we were like in the upper 90s from an accuracy perspective in taxonomy. So the results are actually very, very good. All right, so now that I have talked about taxonomy, finally, let me tell you what taxonomy looks like, right? So here's two examples we made up of taxonomy. One is from manufacturing, and the other one is from e-com. So in manufacturing, as you can see, there could be like, say, multiple levels, right? All the way up to like, what is it? Level 5. So let's see, it's hard for me to read from over here. Maybe, level 1 could be a pump, which is an equipment type. Level 2 could be a centrifugal pump, so like a subcategory or subclass. Level 3 could be an impeller. Level 4 could be maybe stainless steel, 8 inches, and then level 5 could be a particular classification or a code. Now imagine a table having this level of rich and detailed data with all your 50,000 products in it, right? With this type of enriched data, you can do some amazing analytics on it, right? The other example is, there's e-commerce there, but I'll give you an example of a retailer. So not too long ago, we worked with a retailer who had sub-retailers in South America, and they had no idea what the sub-retailers were. Some of them could be like really, really small stores, like literally like a vegetable vendor with a cart. But once they knew, and Alistair will actually do a demo, which kind of is somewhat similar, but once they figured out who the retailer was, they could very, very easily then do cross-sell and upsell. So if it's a chemist or a drugstore, they can do certain things. If it's more of a general store, then there are certain other items that might be relevant. So it has got, as you can see, real business impact. Okay, but then why are we so excited about it today, right? I mean, why now, and what is the compound AI or the agent opportunity? So about last year, maybe right around this time, there was a very famous paper published by Matei and others from Databricks and UC Berkeley titled "The Shift from Models to Compound AI Systems." Quick raise of hands. Have you guys heard about it, read about it, whatnot? No? Some people? Okay. If you have not, it's a pretty good read. A basis of a lot of our work after I saw this paper was actually derived from this. So of course, it talks about a compound AI architecture, which then kind of feeds into agentic systems as well. So a lot of the work we have done in the recent, say, about a year, we have used a lot of concepts and sort of kind of almost inspiration from this paper. So what's kind of the big deal about this, right? So basically, compound AI systems are AI systems that solve tasks through multiple interacting components, including different types of LLMs, information retrievals, APIs, and all that type of stuff. So simply put, it is a very modern architecture with LLMs as just a component, and I write frequent blogs, and in fact, I wrote a blog about this several months ago, about how most modern architectures these days are not LLM-centric, right? So when GenAI came into existence, November 2022, when ChatGPT was launched, soon after the API was available, all the applications that were created, or most of the applications, were kind of LLM-centric. You had an LLM, you had some sort of chat interface, it bounced against the LLM, you got a response. And then the world realized, oh, wait a minute, there's a big problem with that. LLMs hallucinate, they don't have awareness of your data, they only have general information through the pre-training phase, whatnot, and hence the evolution of compound AI, and we have had just tremendous success implementing these systems. So obviously LLMs are not enough. LLMs are powerful, but they're not all-knowing, right? The pre-training phase goes through the general data, which is on the internet, but not your data. So that's kind of the important point. The other thing is, initially there was a notion that throw the biggest hammer at it, right? So find the biggest LLM you can in terms of number of parameters, and hopefully that solves your problem. But that's not necessarily true, right? A larger model size does not always mean better performance or better accuracy. Again, LLMs don't have a memory. You have to provide them memory. They can't access, well, they can access tools, but you have to write the tools, internal, external, all that type of stuff. So now the age where we are shifting, or probably have already shifted from monolithic models to now these modular compound AI systems. So I think that's what we find as amazing. So essentially LLMs, external tools, retrievers, APIs, and logic, and Alistair will actually show us a demo when we bring all these things together into something like which I frankly think is pretty amazing. I mean, people don't realize that it was just impossible to do some of this stuff, like maybe about a year ago or something. The other thing I like about compound AI systems is the best way to design complex systems is to break it down into modular architectures. And this is like a classic example of a modular architecture. The other thing I also like, I was immensely inspired by a quote by Andrew Ng, or one of the presentations I saw of Andrew Ng recently, is you can actually take a GPT 3.5 model, which is an older model, a smaller parameter model, and make it produce the same efficiency and accuracy as the biggest hammer available today. Why? Because you are basically augmenting its capabilities with tool calling and APIs and memory and all that type of stuff. And that really resonated with me. So no longer do you have to chase down the biggest hammer out there. You can use, from an inferencing, quality, cost, whatnot perspective, a smaller model potentially, and then using all these different tools, contextual reasoning, contextual awareness, whatnot, which you will see shortly, you can actually make it into a pretty compelling and a pretty powerful system. Now, having said that, this actually had tremendous impact on our design philosophy, on how we build systems and how we work with clients and how we are actually implementing GenAI systems. So this is how we kind of position the whole GenAI application journey when we work with clients, right? Now, this is a pyramid structure. And again, it's not a strict pyramid, because a lot of the different components and the different things we are mentioning over here can be intermixed and can be exchanged and all of that, right? But one of the biggest frustrations I personally had is when we talk GenAI, and again, maybe this is about a year and a half ago, people automatically related that to chatbots, because that was the world of chatbots and RAG patterns. And I call that as the level 1 application. And again, they're great and they're very powerful. Like if you put one of these in a customer support type center, it can have a huge impact. So I'm not at all against it, but all I'm saying is, a typical RAG pattern, just a RAG pattern with an LLM, think of it as level 1. If you go one level up the pyramid, then we go to what is called as the intelligent, or what we call as the intelligent information platform. So these are slightly complicated system, right? An example of this could be a document extraction system where you upload documents, either batch, real time, extract key value pairs, interesting information, whatnot. Then we get into a reasoning and an acting type of paradigm where now you can have complex context, use an LLM to reason against it and make some business decisions. Maybe about a year and a half or 2 years ago, I was very fortunate to actually work on a business application where we used reasoning. So we would pass health information data, use an LLM with a reasoning type of prompt, and make it reason to figure out a risk rating from a life insurance perspective. So that was a fascinating experience where we did something beyond a chatbot. Then is the compound AI systems. So, and again, that's what the talk is, and you'll see some great examples today. But again, ability to use multimodal LLMs, API calls, tool calling, all of that. And of course, at the top of the pyramid is the agents. This has been the week of agents with everything being announced. We have already been working in agents. We have implemented a couple of iterations of that. And again, this is not a strict pyramid, right? Like, for example, you can use a RAG pattern as part of an agent or as part of a compound AI architecture. But this is just to kind of explain what that Gen AI journey should look like. And of course, all the work we do is all based on the Databricks data intelligence platform, data plus governance plus apps. We build a lot of apps as well in Databricks apps. All right, having said that, now turn for the smart guy. He'll walk us through the specifics of compound AI for taxonomy, and then we'll see a pretty interesting demo. So all yours, Alistair.
All right. So let's go over the core components of what makes up a compound AI system, specifically in this context, taxonomy generation. Of course, you need to have an LLM, and specifically what we're going to highlight is the power of multimodal LLMs. So the ability to handle not just text data as an input, but text, image data, structured and unstructured data. That can lead to some really powerful results, generating product descriptions, attribute classification, and other predictions. Second, you may want to supplement the system with a classical ML model as well. So classical ML models are still around, and they're still going to be there. So they can be used for more narrow tasks like specific attribute or rule-based mapping predictions. Now, external APIs. Of course, we're going to show you how you're going to use your own data in UC to run inference and generate predictions. But what about enriching your data from external sources? So the retailer example that Sudhir mentioned, for example, the data that the client had was really not that useful. It was just addresses, and we don't know the rest about the retailer. So, but what if you connected it to an external API, like the Google Street View image API, where you provide an address and you get an image result back? The LLM can then process that and then give you some more metadata information about what that retailer might do in terms of their own business. So connecting those APIs is definitely something we're going to show today as well. Of course, your internal structured data is very key. So taxonomy has different rules and definitions in each organization. We can any day go to an LLM and ask it to predict taxonomy. It'll give us something. But we want it to be grounded in the values that we recognize in the organization at hand or in the business domain at hand. So tying this system with your internal structured data with taxonomy definitions and taxonomy rules is key. Now, as your data gets bigger, you may want to use retrievers and vector databases to do semantic search to supplement and provide those rules on inference time. And of course, all these are multiple pieces. They have to be stitched together by a controller or a planner block. So this is the sort of the orchestration of all these different components, taking your input and getting those intermediary predictions until you get your final combined prediction. So why now? And why Databricks for compound AI? So Databricks provides some great features that make this system very easy and useful to stand up. So Mosaic AI Agent Framework, of course, allows you a great platform to build AI agents. And it supports multi-turn conversation. It also supports evaluation. And of course, the deployment of those models is just very easy and something which will support us for the batch inference as well. Then foundation model APIs and AI gateway. So like I said, we're going to show multimodal LLMs over here. But how do you make that accessible and easy to use within Databricks? That's where AI gateway comes in. You also have the foundation models APIs, which are ready for you to use. And so you have access to those. You have access to external models like GPT-4o if you use AI Gateway, and even your own custom LLMs or custom models. Sorry. And then AI Query. What I'll show first is going to be real-time inference, but where the power of taxonomy generation comes in is batch inference. So AI Query is a great feature to allow you to do batch inference at scale. And you can basically build workflows that predict taxonomy for a lot of rows of products or retailers or whatever the records are that are missing taxonomy today in your tables. Unity Catalog and ML Flow helps you to track, version, and govern the lifecycle of your models or agents. And of course, allows you fine-grained permission controls and access controls on your data. And of course, Delta Lake and PySpark allows you for inference and orchestration at scale. Okay. The example I'm going to show in the demo is around a clothing retailer. So we're talking in the product domain over here. And this is a reference architecture and what you'll see in the demo. So think about in Unity Catalog, say you have some product data and image data. Now imagine this product data has very little information, at most a few words as a product description, and you have a URL to an image or just the file itself to the image. What can you do with that to actually generate taxonomy and generate this at scale? So that's where you can build, and what we've built over here is an MLflow PyFunc model that you feed in the text and image data as input. The first prediction you get out using your LLM that's hosted through AI Gateway will be your initial taxonomy predictions. So Sudhir showed that slide level 1 to level 4, for example. That's where you would get your first intermediary predictions. But there's a catch over here. How does it know what level 1, level 2 is appropriate to assign? It could just make up something, but we don't want it to do that. So that's where you see the Databricks API block over there. I want inference. We are also sending a call to the Databricks API to read our taxonomy rules definition table. So this could be like a list of allowable taxonomy values, or could be like literally definitions of what level 1, level 2, level 3 is. Because a certain value of level 4 needs to match with a certain level of level 1. There has to be a hierarchy as well. So this helps you stay grounded in that truth and avoids hallucinations. All right, you get your first taxonomy predictions. Then there's a call to a second LLM. And over there, again, you have to read up what are the allowed attributes for those given predictions. Again, it still has the image input, it has the text input, but now you can predict your attributes. So in the case of clothing, for example, attributes could be things like what kind of seasonality is it? Is this a winter item? Is this a summer item? Or so seasonality is one thing. It could be also the material, the color, some things like that. And then finally, the final LLM prediction that can be done is predicting some additional metadata. For this example, and where the external API comes in, we want to know and try to infer what the brand is of this product or this clothing item. Because again, this is a retailer. They don't make their own clothes. They just, it's wholesale. They're just selling different clothing items. And then metadata could be, what are the competitors? Who are our competitors who are also selling this product? So for this example, we're using the Google Lens image search API. So Google Lens, I'm sure if anyone's used Android or even Google Photos on your iPhone, you've probably used that Google Lens feature directly. They have a great API now as well that you can use. You provide an image as an input and you'll get search results. So not only will you provide the LLM your input, your text, text and image data, but also the search results that you get back from Google Lens. And now with all that information, try and predict the metadata. So that's what the final step is doing. And all of this is then stitched together as a final output to Delta tables. Before I go to the demo, one thing I want to say is why are we doing 3 LLM calls or even more than 1 LLM call? It's to minimize the cognitive overload. When you ask an LLM to just predict 20 different things in one go, you don't often get the best results. And that's what we learned with that, the project we were talking about. We realized that once you actually get to break it down into these sequential steps, that's where you're really feeding in the LLM with some proper logic, because you really need to first predict the taxonomies before you then get to try to guess what is the seasonality for that product, because it may not apply if the LLM doesn't know anything about the taxonomy in the first place. So that's the reason for breaking it down into 3 steps. With that, we'll go over to the demo. Yeah. Thank you. Okay, cool. So imagine you are a business analyst and you've been tasked with assigning taxonomy values, attribute values, and metadata values for this new product that the business needs to onboard very, very quickly. So for this example, I'm just going to provide an image input. Again, we're doing clothing. Got a, looks like a shirt over here. Let's provide the image URL. And spotty Wi-Fi, but no, we've got a preview. So before we call the LLM, just want to, this is what we expect to send over. And just going to query our LLM. Now, while that's running, you may have noticed we're using Databricks apps. At Lovalytics, we love using Databricks apps. It's great for basically spinning up something really quick to showcase to your end users, your executives, about an idea you have for a model. We're using a Streamlit template over here. It's connected in the backend to our model serving endpoint that we stood up. And very soon we'll get the prediction so we can see the results. But it's very easy to stand up even if you don't know, detailed HTML and CSS. Okay, so we got some outputs first. And like I said, it takes some time because we're doing a 3-level approach here. So the first, let's look at level 1, level 2, level 3, and 4. We've got men. So the level 1 is just, is it men's, is it kids' wear, is it women's wear, or is it some other accessories? So you can see it's, in this case, it's predicting men. Level 2 is apparels. Level 3, top wear, and level 4, shirts. The backend for this, we're using GPT-4o as the multimodal LLM. You can use another one as well. But I also want to point out this reasoning. So we've actually, we really like this approach of asking the LLM when it makes its prediction to provide textual reasoning as to why it did that. So you can see here, it says that the image that it sees is a men's formal shirt. So based on the rules that we're feeding it from our lookup to the taxonomy rules, there's a category called topwear for level 3. So it's looking at that. That's why it's assigned level 3. And based on its cut and style is what it says. You can see here, it aligns with the men category. And of course, it's a shirt, semi-formal attire. So you can kind of see this reasoning. I think it really helps with auditability in case especially once you get into batch predictions and you get a bunch of predictions and then you realize something is wrong and you want to investigate that. Why not have the reasoning there to understand, what did we feed the LLM in the first place? Did something go wrong, or did the LLM totally just misunderstand what we were providing in the first place? So I think reasoning is something that's for this exercise of taxonomy generation is good to generate. Then the second call was the predicted attributes. So it's predicted the color purple. I think you can infer that from the image. Nothing about it really suggests that it's for a specific season. So it says all seasons and formal usage. Okay. And the last one was the metadata. So this is where the API to the Google image search API comes in. So we are providing that image as an input to Google's Lens API. It's predicted the brand as Reed and Taylor, and we can actually just double check this. Let me zoom in a bit, and you can see here, you can kind of see on the logo, I believe it's a brand from India, that's a Reed and Taylor shirt. So it's been able to identify that. And then it's started listing some of the possible vendors who might, like, for example, competitors who might be selling this product. So Amazon, eBay, and all of this is, again, coming from the retrieved search results. Okay. So this is the app. And this looks great, but what is happening in the back end? So let's switch over to Databricks. Okay. So first off, we'll start here. I mentioned PyFunk. I'm a great fan of PyFunk models, and they have great support now for agents, obviously, because you can customize whatever model you want and log that to MLflow. You're not tied down to the specifics of any library or flavor like scikit-learn or LangChain specifically. You have the freedom to choose what you want and the customization you want. So I'm not going to go in the code in detail, but I'm just going to show some key snippets. We want structured output, right? Our output, even though we're working with LLMs, it's actually tabular data that we want as an output. So that's where structured output specification comes in play. So all these JSON definitions, these are just specifications that, hey, I want these kinds of structured outputs in my response as a JSON object. Because once I get JSON with PySpark, it's very easy to flatten that to tabular data, tabular fields. Okay, I'm going to scroll down a little bit. We have some lookup functions, like for example, we said we had to look up what the taxonomies are. So again, we're using the Databricks, in this case, the statement execution module from the Workspace client, or Databricks SDK rather, if you've used that, which under the hood is just using the Databricks REST API to query your data. And then, of course, we want to load the attributes, filtering for specific levels. So once you get your taxonomy predictions, you want to filter for those and then look up what are the allowed attributes for those taxonomy combinations. And then finally, I'll just use your REST API call. And finally, going right to the bottom, where we put this all together, the predict function. Every ML flow, by the way, every ML flow model, PyFunc model needs to have a predict function. So we have a step one where we get our predicted taxonomy, and then providing that taxonomy as an input, we get our predicted attributes. Finally, the metadata attributes, and stitch it all together, pandas data frame, output, and you're on your way. We've served this as a model serving endpoint. So obviously, you need to provide your credentials for authentication purposes. Otherwise, the LLM is going to try to, or the model is going to try to query the UC without the proper permissions, and nothing's going to come back. So try to make sure you have the right credentials in place. Now let's go to inference. I talked about batch inference, for example. So let's look at our inference data before we get any predictions. So this is some sample data that we have here. You can see we have very basic product descriptions. Some of them are a little bit more detailed than others, but not great. And that's all we have. We have images on the right, all the different links. And in some cases, you may even have missing data here. We worked with the client we were talking about earlier. They also had product information where they wanted taxonomy generated. And out of the 8 or 12 columns that we thought we had available to us, most of them were unusable because of just missing data. And there's just everyone's too busy in the organization to go and clean that up, but taxonomy is still required. So that's where multimodality, at least having one of these inputs and specifically the image, helps. Now let's just look at the use of AI query, like I mentioned. So AI query, as they've shown actually in a few sessions this week at Summit, is really great. So we stood up a model serving endpoint of our own taxonomy demo. Now using SQL query and in a batch inference paradigm, you can now query your endpoint, but providing multiple rows in the input request, and you get your batch output. So if I scroll to the right, you'll start to see you get basically a nice JSON object, a JSON field, which is, you can expand that out, as I've done on the right-hand side here, to tabular fields, which are then ready to go, and you can populate them to your output tables. So this is, I think, a really great way of doing batch inference using compound AI to generate taxonomy. Okay. Switch over. Okay. So in conclusion, where we are today is we've clearly witnessed a shift from standalone LLMs to compound AI and even agentic-based architectures for generating taxonomy. And why does this matter? So, and especially with the architecture we showed over here. We want to reduce hallucination by grounding the system with the right external tools, with the right access to the specific tables in your data, and providing the right business logic as to how it should generate those predictions. And it also increases your precision and adaptability to real-world scenarios. And why is Databricks the right platform for doing this? Like I said, Mosaic AI Agent Framework allows us to create a custom model. That was the PyFunc functionality. It allows us to serve that model using model serving, and as well as the agents deployment SDK. And you have AI Gateway and foundation models that make it easy to access these LLMs within Databricks with the right guardrails that you set up, and also to set up inference and monitoring tables if you need. Unity Catalog and ML Flow allows you to manage the lifecycle of those models in the appropriate way, while also controlling fine-grained access controls. And of course, the power of Delta Lake and PySpark handles the scale, structure, and speed of your inference. So that's where not only are you able to support real-time inference thanks to model serving, but with AI query and Spark under the hood, batch inference is also now very much possible with taxonomy generation and compound AI. All right, I think we have some time for some questions.